Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be introducing Hess's Law, a relationship that relates to the energy changes that can occur in a chemical reaction. So firstly we're going to define what we mean by Hess's Law, this relationship. We're going to look at what we call the deltaH, or the enthalpy change of equivalent pathways. We're also going to look at the sum of deltaH in cyclic reactions, that seem to come back to at their initial state. And then we're going to look at how Hess's law allows us to determine the enthalpy change for any reaction with two main approaches, the graphical method and the equation method. Okay, so what do we mean by Hess's law? So Hess's law was proposed by this Swiss chemist, and here is kind of the statement that we make. So a combination having taken place, that is a chemical reaction, the quantity of heat evolved is always constant, whether the combination is performed directly or whether it takes place indirectly and in different steps. So essentially Hess's law, this relationship that's being articulated here, is a restatement of the law of conservation of energy. So what it's really getting at is this idea that when we're going from a starting point to a finishing point, the energy change that occurs there will be the same no matter whether we go from point A to point C directly or whether we go through some intermediate step B. Okay, or intermediate steps, plural. It's not limiting in that way. Okay, and so there's two equivalent ways that we can be thinking about Hess's law. Okay, so the first one is that this overall enthalpy change, the overall deltaH of a chemical reaction, is independent of the pathway between the initial and final states. So we have a starting point, we have a finishing point, that the overall enthalpy change doesn't matter what happens in between, only about the difference between the beginning and the end. And secondly, it also means that when we're thinking about a complete cycle, a series of reactions where we come back to that starting point, that the sum of all of these enthalpy changes will end up being zero. So as we go round and round the cycle, then in the end that they will all add up to being zero. Okay, so I'm going to unpack how that might look and how that comes about. Alright, so we're talking about this idea of what we call equivalent pathways. So two different paths to go from the same starting point to the same end point. Okay, so let's say we're talking about these substances A, B, and C. Okay, so as we go from substance A to B, we have a deltaH1. As we go from substance B to C, we've got deltaH2. Now they are, remember, just referring to reaction, so heat of reaction. And then we can look at and say, right, what about if we could go directly from A to C? So what's this purple arrow that's down the side? Okay, so if we said that A to B has deltaH1 and B to C has deltaH2, what we can notice is that this substance B isn't present at the end. We've overall gone from A to C, even if we've gone through this middle substance. Okay, and so A to C is this deltaH3, that this kind of purple arrow that's over on the side. But what we're saying is that this deltaH value here, the difference between A and C, is the same as the steps from A to B and B to C added together. That is, deltaH1 plus deltaH2 is equal to deltaH3, this value from top to bottom. Okay, so that's kind of showing Hess's law in action. But what about this idea of around a cyclic reaction? So if we start from a certain point, we cycle all the way back around. So let's say we go from A to B, the same deltaH1 value. Again from B to C, deltaH2. But now we're not considering jumping from A to C, we're now considering what if we would go from C and work our way back up to A, the starting substance. Okay, so A to B's got deltaH1, B to C's deltaH2, we just talked about that. But this one, imagining going from C all the way up to A, is this deltaH4. So this energy change going from here all the way back up. Okay, and so we've seen that B is cancelling out here. And now what we also see is that C cancels out. And so we end up going from A all the way back around to A, which kind of fits. We're starting here and we're going all the way around back up here. And so what that means is that then we cancel that out as well. So in the end, we end up with 0. There's nothing left. So when we're talking about a cyclic reaction that goes around like this, that all of these values going from here down to here and then back up again will add up to 0. Okay, because the fact of whether things are going down or up affects their sign, positive or negative. Okay, and so essentially we're also seeing the same idea if we were imagining that pathway from A to C and then back up from C to A. Delta H3 plus delta H4 is going to equal 0. So the fact that we haven't gone through B in the middle doesn't affect that overall delta H. Okay, so they're equaling 0. That is, that one is the opposite sign to the other. So they're the same in size but opposite in sign. So delta H3 is in the negative value of this increase here. Okay, so that's why we end up with a sum of 0 around a cycle. Alright, so let me show you in action how this works. Okay, how Hess's law can apply. So we're talking about calculating this delta H for this particular reaction, turning carbon into carbon dioxide by reacting with oxygen gas. Okay, but we're proposing that we could go directly, or we can actually go through an intermediate of making carbon monoxide. And we have a delta H value of forming this first step of forming carbon monoxide, CO, of minus 110.5. And then going from CO to CO2 with its own delta H2, minus 283. Okay, and so we're going to show you these two methods that we just introduced before. The first one being the graphical method. So we've got carbon, carbon monoxide, and then carbon dioxide. Okay, so the first step is the formation of carbon monoxide, delta H1. The second step is this formation of carbon dioxide from CO. So this is delta H2. But so then we can see, looking at this approach, that then if we just jump straight from one to the other, going from carbon to carbon dioxide, that we end up with a delta H value, delta H3, of minus 393.5, which is the same as adding these two numbers together. Okay, but what about if we didn't want to bother drawing a graph, or we didn't want to go to that fuss? How could we work this out, or play this out? So the equation method helps us here. Okay, so we list out the two equations, so to form CO and then which reacts further, with their delta H values. Okay, but what we see is that if we add these two equations together, that carbon monoxide cancels out. It's present on the right here and the left here. It's the same on both sides, it cancels out. The half O2s would add up to be one O2 molecule, and then we're left with carbon and carbon dioxide. And our delta H3 is the sum of these two values. Okay, so we've been able to combine these equations so that then we could actually see how this might work for this reaction. Okay, but one of the benefits of using Hess's law is that it's this great now theoretical approach, or this problem-solving approach, to calculate values for reactions we can't measure experimentally, whether they're difficult or even impossible to perform, or haven't been done before. But we can actually use this principle to add up the values of the different steps and then to work it out. Okay, so let's say another example of this is turning graphite into diamond. Okay, we can't exactly do this in a lab. The conditions required in order to do this are monumentally difficult. Okay, but we can still calculate a theoretical value for this process. Okay, and so the way that we're going to do that is we're going to turn both of these substances into the same compound, carbon dioxide, and measure the delta H for each. Okay, so we're going to use that as our kind of joining point. Okay, so to turn graphite into carbon dioxide, minus 393.5 kilojoules per mole. To turn diamond into carbon dioxide, minus 395.4 kilojoules per mole. Okay, so the graphical method, we've got our diamond and we've got our graphite, and so we've turned both of these substances into carbon dioxide and measured these values. Okay, and so then what we are noticing is that when we're looking at this value here, the difference between diamond and graphite is the difference between these two numbers. We have minus 1.9 kilojoules for every mole. And so we've been able to use this graphical method to work that out, even though you couldn't do that experimentally and measure it. let's have a look at using the equation method. Okay, so we have the first equation for the formation of reaction of graphite, and then the reaction of diamond. Now, if we just add these equations together as they are, we're not actually going to get this overall one up the top. What we have to do is we've got to do a little bit of smart thinking, and that is recognizing, okay, well, I need graphite to be on the right-hand side, and in this equation it's on the left. Why don't I just reverse the equation and then therefore reverse the deltaH value? Because we've recognized that this value will be the same for the same kind of process. The difference is the same. The sign will change. So it'll go from negative to positive. So let's reverse that first equation with a positive deltaH value. So going from carbon dioxide to graphite and oxygen would have a deltaH of plus 393.5 kilojoules per mole. What that now means is that now we have an equation that we can add. So we have our original diamond equation, we have this reversed equation in red, and now we can add our equations together. Our oxygens and our carbon dioxides will cancel, and we add together our deltaH values to get our final resulting value, which is minus 1.9 kilojoules per mole. So we reversed an equation so we could add them and cancel out the things that weren't supposed to be there, and then we added together our deltaH values. But just remember that to be careful to change the sign if you reverse the equation. Okay, and so then we can ask ourselves the theoretical question of, well, what would the value be to turn graphite into diamond? We know that it should be 1.9 kilojoules per mole, that it's the reverse of that first process, and so we would take that value and reverse the sign. Okay, so we introduced what we mean by Hess's law, this idea that the overall enthalpy change or change between reactants and products is independent of the pathway that it takes to get there, or however many steps it takes to get there. Okay, we looked at the fact that this helps us to calculate the deltaH of equivalent pathways. So, whether we go directly or we go through intermediate steps, and we can make those calculations. We also saw that it means that the sum of the enthalpy changes in a cyclic reaction is 0. And we use two approaches, the graphical method and the equation method, to determine the deltaH for any reaction based on established data. Being able to manipulate equations and reverse them and change the signs and adding deltaHs to get the answers that we're after. Alright, thanks very much for watching. Bye for now.